Hi, welcome to my class again. In last couple of hours, we learned both the Kalman filter for linear error model and also the Kalman filter for nonlinear models. But now is the time for us to apply the filter to the GPS. So let me give you a little story about how this course and this module started. That's in 2005. I had a conference in US Virgin Island, St. Thomas. That's a beautiful place. If you have a chance, you should go. And I was bored and then went into a workshop talk about a GPS. I never heard it. I know what is GPS, that's all. But the talk really instantly attracted my interest. The presenter said this: look, you got 5 or 6 satellites hanging up on the Earth 26,000 kilometers above. But by using the signal processing, we can pin down your position in a few feet because our computational model. Wow, I said, that's the math I wanted to learn, you know. And then I followed this guy's slides, and they come back, learn the so-called filter, and of course I know least square, now that's 200 years old. And no surprise, the whole technology of computation built up how you're going to minimize error. The Kalman filter is nothing more than a double optimization. Why double? Because when you use the Kalman game, you really optimized both the prediction model and also the measurement model. And then you do the iterative calculation. But today, you're going to see the GPS, how the GPS used this idea to produce the most accurate calculation. You know, if you think about, let's say the error is 3 meters, that's actually smaller, 3 feet. Then it's 1 meter. But compare the distance from the satellites to the receiver, that's 26,000 kilometers. Just divide, you know, how accurate is that? Anyway, let's briefly introduce what is the GPS architecture and how do we measure the distance, and what is the 2 algorithms. Actually, I'm going to introduce 3 of them. One naive solution, another one is based on Gauss's least square and the Newton's method. The third one is the extended Kalman filter. Yeah, somebody's first time here. Anyway, look at the architecture of the GPS. And the GPS is called the semi-synchronized satellites. The orbit, again, I said, is 26,000. Around that, you have your homework about this, kilometers. And it rotates around the Earth twice per day. And if you look at those arbitrary orbits, you can see there's probably 28, 30 those satellites around the Earth. And they're all, I think there's 6 of orbits. Each one have 60 degrees to the center of the Earth. Well, for us to get the GPS position, we need to pick usually minimum 4 of those satellites signal. Usually 5 to 6 is better, but the minimum is 4. We're going to see why. Well, that's a brief history. The first time the States launched the 28 of this GPS satellite, that's in 1989, and it weighs 900 kilograms, and the cost is 43 million each. And the 21 in 8 years later, and the 12 after another 8 years. So you can see the GPS lifespan usually is designed for how many years? 7, 10, 15 years. So after 15 years, which year we need to do another launch? 2005, then it's 2020. All right, we have probably at least 28 in service. 24 is the good number. So how the GPS can help find your position? Let's start from a naive solution. We all know it's based on the distance from the satellites to the receiver, to the user. Well, the distance is measured by electronic signals, which traveling about 300,000 kilometers per second. And when the GPS satellite sends the signal out, they have a timestamp, and when it is transmitted. And when the receiver receive it, and you know the time difference, based on the time difference, you know how long the signal traveled. And then that you get the time difference here. Multiply the speed of light and squared. These are the distance square on the right hand for all 3 equations. So if we think our position is x, y, and z, we have 3 variables. And then we need 3 equations to solve it. If we have 3 satellites, then you get 3 equations here. The all distance formula. That's the x minus the x of the satellite 1, y minus y to the satellite 1, z minus z1, and then you get this. Well, obviously, we can solve this algebraic equation analytically. Then let's observe what this idea is. So the satellite sent the signal to the receiver, and then the satellite give the time ts. The receiver get the time, when I call it TUs. And then the difference between the 2 times is the transition time, tau. Then is the TUs minus TS. So typically, it's between 70 to 90 milliseconds. Then the signal arrived to the receiver. Based on the distance, if the receiver is here, let's pick a 1 point here. And then you got 3 circles. 1, 2, 3. 3 different distance. You know, 3 circles, two spheres intercept into a circle, and then 2 circles intercept into 2 points. So actually 4 points. But you don't have ambiguity because you have to live on the surface of the Earth or around the Earth. Then you probably think, okay, now I can solve it. Then you get your solution. Well, this naive solution gives you the basic idea how GPS works. but it's really not how the computation works. Next, let's see. Hey, why I call this solution naive? Just think for a minute. Why it's naive? Why it does not work? Sounds all fine. We need the 3 variables and the 3 distance. Give me 3 equations. You solved it, and you can even observe it from the graph. Well, the real problem, as we said, is the word error. What error you're talking about? Now, you check all your watch to see the time. If your time is the same as the other guy beside you's time, and when you look at this, you see, whoa, we probably are different by minutes if it's not seconds. But let us think this way. In case our watch have 1 millisecond error, and then times the speed of light, a millisecond means your distance error will be 300 kilometers. Well, if your GPS have 300 kilometer error, that's worse than data ranking. So that's why naive. So it's most likely, unless you pay $1 million for your watch, that's for the national lab, and you won't get the watch have less than 1 millisecond error.